In this video, I want to have a look at the second derivative of a function and what it tells us about that function geometrically. So we already know that the first derivative of a function represents the gradient of the tangent of a function, and it tells us whether that function is increasing or whether it's decreasing. So the second derivative has the same relationship to the first derivative as the first one does to the original function. So it's going to tell us the gradient of that first derivative. So it's actually telling us the gradient of the gradient, which means that what it's telling us is whether or not the gradient is increasing or decreasing. So if we have that our second derivative is greater than 0, that means that the gradient of our function is increasing. So you can see here that we've got a gradient that's small, it's close to 0 here, and as we move across, it's getting steeper and steeper. So that means that the gradient is getting bigger or increasing. So if our second derivative is less than 0, that means our gradient is decreasing, as you can see here. So as we move across, the gradient is getting more and more negative. So the other way you can look at this is that the second derivative tells us about the concavity of the curve. If the gradient is increasing, then that is a concave up curve. If the gradient is decreasing, then that's going to be a concave down curve. To summarize those points, if our second derivative at a is greater than 0, that means that the function is concave up at x equals a. If our second derivative at a particular point is less than 0, that means that our function is concave down at that point. Now the third case is a little bit different. If our second derivative is equal to 0, we don't actually know what happens there. There's lots of different things that could happen. So we need to look a little bit closer to be able to tell what's happening at that point. So one of the situations where our second derivative will be equal to 0 is if we have a horizontal point of inflection. So looking at this example here, we know that right here we have a stationary point and it's a horizontal point of inflection. And our second derivative is going to be 0 there because our curve is changing from being concave down to concave up. So because the concavity is changing, that second derivative will be equal to 0. But that's not the only situation where our second derivative might be 0. Another couple of examples are this one here. So at this point right in the middle here, our second derivative would be equal to 0. And this is actually called a point of inflection, but it's not a horizontal point of inflection because it's not a stationary point. But it's still a point of inflection because the concavity is changing. So this section here is concave down, and this section here is concave up. In this last one, it looks kind of like a parabola, except down the bottom here it's a lot flatter. So this is actually the curve y equals x to the power of 4. And right at this point just here, our second derivative will be equal to 0 there. And in this one, it's not changing concavity. On the left, it's concave up. On the right, it's concave up. But there's still a point there where the second derivative is equal to 0. So if we get that the second derivative is equal to 0, we need to use a table of values and have a look at what's happening to that curve on either side to figure out exactly what's happening at that point. So our first example asks us to determine whether the following curves are concave up or down at x equals 1. So to do this, we're going to find the second derivative. So for a, we've got this function f of x equals x cubed minus 5x squared plus 4. So we're going to differentiate once, and we'll end up with 3x squared plus, nope, not plus, minus 10x. And differentiating a second time will give us 6x minus 10. So we want to evaluate that second derivative at x equals 1. So we're going to find the second derivative at 1, which would be 6 times 1 minus 10, which will give us minus 4. So therefore, our function is, because this is less than 0, therefore our function is concave down at x equals 1. If we have a look at b, we have the function y equals 6x to the power of 4 minus 2x to the power of 5. So again, we're going to differentiate twice. So our first derivative would be 24x cubed minus 10x. And our second derivative, that should be 10x to the power of 4. Our second derivative would be 72x squared minus 40x cubed. Now we want to find that at that same point at x equals 1. Right, at x equals 1, our second derivative is equal to 72 times 1 squared minus 40 times 1 cubed, which is just 72 minus 40, which would give us 32. So because our second derivative is positive, that means that this function is concave up at x equals 1. Our second example is a little bit more complex. So we're asked to consider the function y equals x to the power of 4 plus 4x cubed. And the first part of the question asks us to determine the nature of any stationary points. So that means that we're going to find where the first derivative is equal to 0. So for part A, our first derivative, so this is our function up here, if we differentiate that, we would have 4x cubed plus 12x squared. To find the stationary points, we're going to set that equal to 0. And then to solve that, we're going to factorize by pulling out 4x squared as our common factor. And then we'll end up with x equals 0 and x equals minus 2. So those are the values for the coordinates, should be a plus 3 and a minus 3 there. Can't do my division properly. So those are the x coordinates of our stationary points. Now we also want to find the y coordinates. So to find those, we're going to sub these x values back into our original function. So substituting 0 into this original function would give us 0 to the power of 4 plus 4 times 0 cubed is just 0. And substituting minus 3 back in here, if you put that in your calculator, will give you minus 27. So we know that we have two stationary points, one at 0, 0 and one at minus 3, minus 27. We want to determine their nature. We actually have two ways of doing that now. We can either use the second derivative or we can use a table of values and make it up for the first derivative. So let's have a go at using our second derivative. And so if we find our second derivative is going to be equal to, so we're differentiating this one again, we'd have 12x squared plus 24x. Now at x equals 0, our second derivative, if we put 0 in here, our second derivative is going to equal 0. And what we said about that is if our second derivative is equal to 0, that doesn't tell us enough information. So we're going to have to do something different with this one in a minute. But we can have a look at the other one. So at x equals minus 3, our second derivative, so we're going to substitute minus 3 into here, and we're going to end up with 36. So substituting that in there gets us 36, and because that's positive, it means it's concave up. So that's told us enough information about one of our stationary points, so I'm going to draw it up here. So we have minus 3, minus 27 as a stationary point. We know that it's concave up, which means it's going to be a minimum point. So it's going to look like this. Our other one that we didn't have enough information about, so now we can revert back to the other way of doing it and draw up a table of values and figure out the first derivative either side to see if it's increasing or decreasing. So if we draw up our table of values, we've got x and we have our first derivative. We need those three values, so we've got 0, we may as well pick minus 1 and 1. So we know this is 0, we know it's horizontal point we know it's a horizontal point at that point. If we substitute minus 1 into our first derivative into here, we're going to end up with 8, which is positive, so we're going to have a positive gradient. And if we substitute 1 into here, we're going to end up with 16, which is positive as well. So because it's increasing on both sides, we're going to have an increasing point of inflection at 0, 0. Part B of this question asks us to find the coordinates of any points of inflection. So we've already found one of them because it also happened to be a stationary point. But there might be other points of inflection in there as well. So remember, a point of inflection is just where the concavity changes from being positive to negative. So where there's a point of inflection, our second derivative is always going to be equal to 0. So we're going to find our second derivative, just rubbed it off, but our second derivative was 12x squared plus 24x. We want that second derivative to be equal to 0. So we're going to have 12x squared plus 24x equals 0. We'll factorize out that 12x as a common factor. And we'll end up with x equals 0 and x equals minus 2. Now we already know about the point of inflection at x equals 0 because it also happened to be a stationary point. But we don't know about this one. So we're going to investigate this one a little bit closer and see what's happening on either side of it. So we're going to draw up a table of values. So we're going to have our x values and we're going to have our y second derivative values. So we're going to have minus 2 in the middle here, and we may as well pick minus 3 and minus 1. Now we know that second derivative here is 0, but we want to know on either side whether our curve is concave up or down. So if we substitute this minus 3 into this equation here, we would end up with 36, which means it's concave up. And if we substitute this bit into here, we would end up with minus 12, which means it's concave down on that side. So concave up, concave down. All right, the last thing I've forgotten to do there is find the y coordinate of that point. So at x equals minus 2, we can find our y coordinate by substituting that back into our original function, and that would give us minus 16. So we have a point of inflection at minus 2, minus 16. So part C of our question then asks us to sketch our function. So we're going to put in our stationary points first. So at 0, 0, we had an increasing point of inflection, which means it's going to come like this. And at minus 3, so we'll put minus 3 over here, minus 27, we had a minimum point. Got a minimum point there that's going to look like this. We also found out that we have a point of inflection at minus 2, minus 16. So at this point here, our curve is going to change from being concave up to being concave down. So up on the left and down on the right. So we can join those together now. So this is going to come up this direction. It's going to curve and start being concave down here. Then it's going to come up this way. Oops. And then it's going to come up here as well. The last piece of information you might want to find out about that graph is this X-intercept, and we could do that by setting y equals 0 in our original function, which would give us 0 equals x to the 4 plus 4x cubed. We can factorize that, and that would tell us that either x is 0 or x is equal to minus 4. We already had the 0, but that just tells us this point is at minus 4 here. So that's having a look at the second derivative and what it means geometrically.